Hello and welcome. Today we're going to be talking about Chapter 0, Section 1 on sets. Our main objectives today are using set notation to denote elements, subsets, and complements, as well as finding the intersection and unions of sets. So let's talk about set notation here. First off, let's talk about what is a set. A set is going to be some collection of objects. It could be anything. It could be states, it could be numbers, it could be letters, it could be cookies, or there's a lot of things. It's just general an object. And each of these objects is referred to as specifically an element. So, and we're going to use the Greek letter epsilon, lowercase epsilon, for this. And this epsilon means the element of. And I'll show you how to do that in just a second. So let's do an example. So let W be the set of whole numbers, W for whole numbers less than 10. So let's think about this. W will be that whole number set. It's capital is equal to, and set notation will always have a kind of a squiggly bracket symbol. It has to be those. It's not any of your normal parentheses. Now, whole numbers, if we want to think about those, I underline those in blue. Whole numbers start with this. So whole numbers start with 0, then go to 1, 2, 3, and keep going on forever. There, you're counting numbers, and we're including 0. So we're going to start with 0, 1, 2, 3, 4, 5, all the way up forever and ever and ever, going up by those nice integers. They're even or positive integers, including 0. So let's think about that. What are the even whole numbers that are less than 10? So we're not including 10 because less than 10 can't include. We would say equal to if we wanted to. But even whole numbers, even would start with 0 because 0 is technically even because 0 times 2 is a way to define it. 0 times 2 is 0, which is an even number. Even numbers are any number multiplied by an integer times 2. So we'd have 0, we would have 2, we have 4, we have 6, we have 8, and we cannot include the last one of 10 because it's not equal to, and then we close our bracket. So this is what we call set notation, a capital letter to define what the set is. We have the set brackets, and then each element inside. So all of these are elements. So 0, 2, 4, 6, and 8 are elements in the set. So that would be where this element symbol comes from. And how I could say it is like 0. Let's say 0 is going to be an element of W. And that's how I could use that notation of element of. So let's do some examples here. So set notation, let's use this set notation to write the elements of each set. Then we're going to determine if the statement about the set is going to be true or false. So let's find n, which is going to be the set of natural numbers less than 7. Natural numbers, if we think about natural numbers, are your counting numbers. Natural numbers are the whole numbers, but without 0. So in this case, n is this set, and we're going to do n is equal to that squiggly bracket. And then we do not include 0. So then we just start with 1. Like our counting numbers, you start counting 1, 2, 3, 4, 5. So we start there. So we do 1, 2, 3, 4, 5, 6. We're less than 7, so we do not include 7. So we close this bracket right here. And then it's asking, is 5 an element of that set n? And that's in fact true, because 5 is in fact right there. Now, let's do another example here. So the set S is equal to, let's see the squiggly brackets, all of the states that border Minnesota, which if you don't know, we have North Dakota, we have South Dakota, we have Wisconsin, and lastly we have Iowa. And I'm just going to write that one out. It's pretty short. And close the bracket. Now, is Ohio part of that set? Well, that is false. Ohio is not an element of. And again, we could just say Ohio is not an element of S. And that's one way we could write it as not being part of it. But it's asking true or false. So the last one here is we're going to use D for the set of days. So we're going to label it like that, is equal to the squiggly set. Days of the week that begin with T, which is Tuesday and Thursday. Those are the only two ones that start with a T, unless you're thinking about today and tomorrow, which you could write those. But we're just saying those 7 days of the week, which in this case is Monday part of that. Well, that is in fact false. So let's go talk about sets some more. We're going to talk about something called the union. So we have the union of sets, or the intersection of sets. We're going to have the union of sets A and B, which we're going to say union as, let's do A and B here. So A union B, which is right here. That's how we write it. A union B is kind of like a U for union. It's essentially putting all of the elements together. So it's like all of the elements of A, all of the elements of B. We put them together into one big set. So it's putting both sets together. It's kind of like addition in some case, but not really. You don't want multiple of the same thing. So it's like if I have A, B, and C, and then C, D, and F, I'm going to not include C twice. I only want it one time. Now, intersection is where do they intersect, or where do they share, where do they cross, where do they overlap. So A intersect B is what we're going to use for that. Again, union would be the U, and then intersection would be the upside down U. It's where do they overlap, what do they both share. So the keywords are here are overlap. What do they share? What do they have in common? So these are other things that we can think about as synonyms. So here are a couple examples here for union and intersection. And if by chance anything ever gets nothing, we're going to use this. This means the empty set, which is this symbol right here. It's a 0, basically with slash through. Or the idea is it's a set with no elements in it. So either of those technically means the empty set, which can happen. So in this first case, we're finding the union, which that's why we have the U thing. We're going to have to make sure we have the squiggly symbol, and we're putting all of the numbers together. And I would love you to put it in least to greatest thing. So if we look at set J and L, we're going to take all of these numbers and just make one list. And we're not going to duplicate. So we have a -2. The next one is a 1. Then we have a 2. Then we have a 3. We have a 4. We have a 5. We have a 6. We have a 7. And then lastly, we have an 8. And then I close my bracket. And we have commas between every one to identify this is an element, this is an element. All of those are elements in both of those. Now, I'm not going to write 5 twice. We only write it once. Now, the 5 is special. Where they both share, overlap, have in common, that is actually that intersection, which is right here. So they, in fact, intersect at only 5. They only have the 5 in common. So that would be my answer for that. So let's go ahead and interpret a Venn diagram of two different sets. So we have softball and volleyball, people playing that. So this diagram shows members for softball club and volleyball club. Use this diagram to answer the following questions. So these are people who are in the sports of softball. These are the people in the sports of volleyball. And then where do they overlap? They both are doing that. So how many people are playing in softball? Well, the whole circle, this whole circle represents where they all play softball. So we have to count all of those names. So we have 1, 2, 3, 4, 5, 6, and 7. So there are 7 people who are playing softball. So now, how many people play both volleyball and softball? Well, if you think about volleyball, volleyball would be this whole circle here. Now, the idea is, where are they overlapping? So this is where they're both sharing or playing two different sports. So Maya and Deborah are both playing softball and volleyball, which is 1 and 2 people. There's only 2 people who play both. That's that and, the intersection. And now how many people are going to be playing softball but not volleyball? So the idea is we don't want the volleyball people, so you're kind of canceling out or taking these ones away. And these ones are playing softball, but they don't play that. So it's just these 5 for those right there. So this next question here, example 3, we have 3 different circles interpreting Venn diagram of 3 different sets. We have some people on Spanish, dance, and computer. So these are the clubs. Let's answer the following question. What clubs is Tom a member of? So let's look at where Tom is. Tom is right here. He's only in this part right here, which is in the computer. The other circles, dance and Spanish, are not encapsulating or around Tom, so it's only going to be part of the computer club. So he's only part of one club. Now, how many members or students are part of the computer club but not the dance club? So let's look at the computer club. So let's highlight all of the computer club here. So I'm going to highlight all of computer. So we have this whole thing is computer. So let's make sure this is all the computer club. Now, we do not want, but not the dance club. So the dance club is over here. So this is my dance club. So we don't want any of those names. So how many people are not going to be part of the blue, but are part of here? Well, there's only 2 who remain inside of this purpley magenta color. So that would just be 2 people. We only have 1 and then 2. Now, which students are in the Spanish club, but not any other club? So again, we don't want anything else. So if we think about this, Spanish club is that whole circle, but we only want the stuff that's not attached to the other circles, which is just this part here. So again, this would be 2 people as well.